All right, welcome everyone. I am JJ. Let's go ahead and tackle an example problem. So we have the objects shown are beam A, B, C, supported by a pin here at C, and by a cable that goes from B up to D. Let's find our support reactions. So let's start out there. Anytime we're looking for support reactions, we know we're going to use the equilibrium equations, which means I should make a free body diagram. So let's draw a free body diagram of this. We can model our beam just as one straight line. Over here at C, I should put in a CY for the pin and a CX for the pin. I'll guess up and to the right. Again, I could guess anything I want here. The math will let us know if we were correct or not. At point A, I have 12 kips going straight down, 12 kips, and I have 40 kips going to the left. So let's get that in there as well. 40 kips. Over the next 3 feet, I have, so this is 3 feet, I have a rectangular distributed load. So let's model that in. Just a handful of lines coming straight down. Getting that in there. It's 3 feet wide, and our height is 8 kips per foot. 8 kips per foot. At point B, I hit my cable, BC. I should assume it's in tension, so going away from my free body diagram, going up and to the right. Cables are always in tension. Don't forget that now that we're hitting this point. But we can call that member or cable FBD. Let's call that FBD. Or TBD or something in there. 3 feet past that, I get to an applied couple moment, 18 kip feet. So we'll put that one in there. It's going clockwise, so we'll just draw in a clockwise rotation. 18 kip feet. That's 3 feet from B and 3 feet from C. Well, that's everything for us. I have 1, 2, 3 unknowns, 3 equilibrium equations. I can find everything in here. So let's go ahead and apply equilibrium. So we'll come up above and just go for it. If I have some moments at C, I'll get rid of both CX and CY. That'll let me find FBD. I could also, some moments here at B, I would get rid of FBD and CX. I could find CY out from here. There's a bunch of ways we could solve this. Just pick one and go for it. Again, I'm going to have some moments at C. So with positive going counterclockwise, let's sum up our moments about point C. That's going to get us, well, this 12 kips will cause a counterclockwise rotation. So put it in as positive. 12 force times my distance, 3, 6, 9. Times 9. My distributed load will cause a moment. It will be counterclockwise. So again, we'll put it in as positive. And I need force times area. We're adding because it's counterclockwise. The force of a distributed load is, we need force times distance. The force is the area. So that'd be, for the area of a rectangle, it's just base times height. So plus force, 3 times 8, times my distance from C to the center of the rectangle, to the dead center of the rectangle, will be 3 plus 3 is 6, plus halfway in. Plus half of 3 is going to get us to 7.5. And then finally, the last thing I have is FBD. The X component, not the last thing quite, but the X component of this is going to go through C. The Y component is going to cause a clockwise moment. So minus, we'll come to the next line, minus force times distance. My force, we should label the angle here. This was a 3 vertical, 4 horizontal, 5 is our hypotenuse. Triangle that it acts along. 3, 4, 5. So the Y component will be 3/5 of FBD minus 3/5 of FBD. That's our force. And our distance is going to be 3 plus 3 times 6. And then our actual last thing in here. I have an applied moment on here. 18 kip feet. It's 3 feet away from C, but that doesn't matter for us. Because it's already a moment. Moment times distance doesn't get us moment. I just add or subtract this. It's going clockwise, so I'm going to subtract it. Minus 18 gets us to 0. Which if I solve that, I have FBD as my only unknown. We will get that the member FBD is 75 kips, and it's in tension for us. Cable should always be in tension. That's going to be our first answer. From here, I still need to get Cx and Cy. I can just sum forces in the x and the y direction to get those. So summing my forces in the x direction, I have Cx plus the x component of FBD, or plus the x component would be 4/5 of FBD, but I know FBD, it's 75. So I'll put it in my known value, times 75. The only other thing I have in the x is this 40 kips. It's going to the left, so subtract it. Minus 40 is going to get us to 0. If I solve this for Cx, I'm going to get a negative. Cx is negative 20 kips. Which that negative tells us I guessed the wrong direction here. So we'll put in our dashed arrow, recognizing that it's really going to the left, and report as a positive. Cx is really a positive 20 kips. We got negative when we assumed it went to the right. So changing our sign, making it positive, we change our arrow. It's really going to the left. That'll be our second answer. Finally, I can sum forces in the y, and I'll get my Cy figured out from this. So if I sum my forces in the y direction, I have Cy going up. I have FBD going up, so plus 3/5 of FBD, 75, minus my distributed load. It's going straight down, so just minus the area, minus 3 times 8, minus my applied force, minus 12, is going to get me to 0. Which, adding all of that up, I'm going to get Cy is negative 9 kips. That was negative when I guessed it went up, so it's really coming down here. Our answer, reporting as a positive, should be a positive 9 kips, and we'll get the correct direction. It's really going down, which would be our final answer for our problem. Hopefully this was useful for us. If it was, hit our like and subscribe buttons. Stick around, watch more videos. Let's get you an A with JJ.